Hi, today we will talk about ground planes, transmission lines and multilayer PCBs. Ground planes are big planes of ground on the PCB that are having several advantages. Like, for example, they are minimizing current loops because the current can flow just below the line and therefore it makes the smallest possible return path. Ground planes also decrease the impedance of the ground and therefore they are minimizing the so-called current generated common mode noise. And of course, ground planes also act as a shielding to prevent the noise to spread around and cause EMI problems. And these ground planes can be used in double layer PCBs or multi-layer PCBs, and we will talk about this today. First, we will start with the differential currents in PCBs. Each PCB that contains some high frequency current, that current of course runs in loop, and that loop, let's say this is the current that runs in the loop, and the area of that loop then causes some noise at a certain distance. And that noise is proportional to the area, frequency, and current, of course. And I think here is frequency squared even. So when the current increases and the high frequency portion of that current increases, the noise increases fast, and the area can be minimized by the appropriate routing. And of course, the high frequency part of the current can be minimized by increasing the rise times of the signals in these loops. So first, as a PCB layouter, one should minimize the current loops as much as possible. So the first question you should ask yourself is how to identify these current loops, or with other words, where does the current flow? Well, the current flows in lines, in tracks that connect to two parts. And here I'm showing you the digital current loop. So this is a digital source, let's say some microcontroller or some other digital interface that changes logic level between 0 and 1. And that current that is caused by that runs on that track from the source to the load. Now, loads in digital circuits are usually high impedance, so they do not contain any resistances whatsoever to ground, but they do contain input capacitances. So when the voltage changes between 0 and 1, the current that charges this capacitor flows through this line, and then it returns back on the ground. But it does not stop here. Well, the power supply that is generating the logic 1 through that output circuitry comes from the voltage source. And that voltage source is also grounded. And now the current continues and finishes here. So that current loop would actually go all the way to the input voltage source. Now the question is how to minimize that current loop. Of course, first action we already taken is that we used bypass capacitors. So putting a bypass capacitor between power supply and ground, you actually minimize the current loop to that point here. So that current loop then that comes from the power supply is no longer active here. But this current loop still remains. So to minimize it even further, we have to provide a return path as close as possible to original line back to the source. And the same holds when you change logic 1 to logic 0. Then this capacitor is discharged through the output of this source. The output is connected to ground, and the discharging current flows here like that. So this is then the loop area of the discharging current. And here, as you see, the power supply network doesn't play a role. So we know how to place bypass capacitors by now, so there is not a problem with that anymore, but we still have to route these signals so that these current loops are as small as possible. And you should know that, of course, minimizing current loop in general is not possible for every single signal. So you have to take care only for those who are the high speed signals, those who carry high frequencies. Okay. In order to understand these current loops, one should understand another phenomenon which helps a lot with the forming of these current loops, which is called skin effect. So what is a skin effect? A skin effect is that high frequency current tends to flow at the surface of the conductors. Why is that so? The current generates magnetic field. And if the current is running in the middle of this conductor, the surrounding magnetic field forms so-called inductance. So if the current would then be flowing on the surface of the conductor, there would be less surrounding magnetic field, therefore less inductance. So to be short and precise, the current that flows on the surface feels less inductiveness, yes. So, where does that current flow then? Well, the current flows where it feels the lowest impedance. And the impedance is actually a sum of two terms, at least in a wire. That is the resistance plus the inductance. So if the frequency is very low, then the current would flow all over the cross section. If the frequency gets high, the inductive part prevails, so the resistance does not play much role anymore, and the current now tends to flow to the surface of the inductor. But then if it flows on the surface of inductor, like here, then the resistance also increases. So resistance is also dependent on the frequency because of the cross section getting smaller. The cross section is proportional to the one of the frequency. So the frequency gets low, the high, the cross section goes lower and lower. It's because the current tends to flow towards the surface, and consequently the resistance goes up. So again, we have a resistive part which then changes with frequency as well. So the current then finds the path which is the most optimal in terms of the energy. So what is that path? That how to say, the thickness of the layer at which the current flows is determined by this frequency, and it's it depends on the permeability of the material, the frequency, and the specific conductiveness or resistance of the material. This is the specific resistance. So that's the specific resistance of material, different materials: copper, tin, silicon, and mu metal. Mu metal is a high permeability metal. And here are the skin depths at different frequencies. As you see here, the skin depth at 100 megahertz is 10 times lower than at 1 megahertz in copper and other materials as well, and depends on the specific permeability of the material. As you see in case of mu metal, the skin depths are really small. So in order to understand the skin depth, you have to know the permeability of material and the specific resistance. And high resistivity or high conductivity materials such as copper have lower skin depths and high permeability materials as well. Now, if the material was ideal conductor, such as superconductor, the current would only flow on the surface of that material. From this skin effect, one should understand two effects in case of PCB tracks. The first is this effect is called proximity effect. The first is in case of differential currents. Differential currents flow in the opposite directions, and if they flow on two tracks, they tend to form the smallest possible loop. So differential currents would flow close to the surface, as close as possible to each other. And this type of magnetic field here, or this type of current would have the least inductance because of the least area. forming. If you have common mode signals, like here, which flow in the same direction, they would tend to flow to the outer surface of these two tracks, forming the least inductiveness or inductivity in that way. So, to sum up, rules of thumb say that AC current will only flow at the outside surface of the conductor. The 35 micron copper, if you check the skin effect, it starts at around 3.5 megahertz at 35 micron copper. That can be calculated from the skin depth here using the copper thicknesses. So 35 microns at 2.5 megahertz or 3.5 megahertz you would get in the range of 35 microns. The skin effect decreases if the effective inductance, so the skin effect decreases the effective inductance, so the skin effect helps you to decrease the inductiveness of the loop. The small diameter wires or thin tracks have larger inductance. The wider traces have lower inductance. And the AC currents in the opposite, running in the opposite direction, so the differential currents attract each other. The common mode currents are flowing out at the outer surface. And the energy that is emitted in the EMI sense are increasing with the area of the loop that you create in your designs. And these magnetic fields will always find a way how to get out of your circuit, and they will cause EMI problems. So you should keep them as small as possible. The skin effect is also shown here. Here we have a track 10 centimeters long that has half a millimeter width at 1 ounce of copper, so 35 microns of copper. It has around 100 milliohms and 60 nanohenries. Now that would have around 11 ohms at 30 megahertz. If you shorten it by half, so 5 centimeter long track, it would have half of the inductance and half of the impedance. That's clear. If you make it 4 times wider, so 2 millimeter wide, the inductiveness or the inductance, the inductance and the impedance would be approximately halved as well. So it has to be 4 times wider to make half of the impedance. And if you take 2 wires and drive in the same direction the current and make them 1 centimeter apart, but only with the original thickness, you would get approximately the same results. So, because of the skin effect now, the current tends to flow on the outer surface of these 2 wires, and since they are further apart, the inductiveness, the inductance is less. Okay, let's go now to some PCB design. We know that we have skin effect, we know that currents tends to run in loops, and of course they are tending to form the smallest loops possible. And we will start with a 30 or 40 years old PCB designs. 2-layer PCBs with digital integrated circuits. This is how the first computers were made, even those which were also in my times when I had my first computer, the computer was made like that. It was running at 8 megahertz, and if you press the turbo button, it may run at 12 megahertz, and that was the maximum frequency of that circuits also. So, in that times, the digital integrated circuits were through-hole, and they were placed very regularly. And this regular placement allowed the tracks to be placed really regularly as well. So there were 2 layers PCBs, and we had 1 layer on bottom and the other on top. And all tracks on bottom were, let's say, horizontal, and all tracks on top were vertical. So what we have here, we have ground, and vertically connected ground. And then we have power supply, and vertically connected power supply. and these are bypass capacitors. And this way of placing and the routing is called orthogonal signal routing, because all the tracks were following the strict rule of being horizontal on bottom and vertical on top. And by that you were able to reach any point of your PCB just by following this simple rule. Vertical on top, horizontal on bottom. And each of these tracks forming power supply and ground opened a window in which a digital IC was placed and routed. So let me now follow one example of a loop. So let's say I have to change the color here. I will choose, probably it would be better to choose yellow, yeah. And let me start, let's say, here. So here is the source of my signal. The source is actually taking the voltage from power supply. So if I want to make logic 1 on that point, I would take current from power supply, then it will go into circuit and then run to this line here. Then it will go inside the chip and then go to the ground and here and return back to my original capacitor. So this is a high frequency loop formed because of that single track. And that loop changes size quite a lot if I take, let's say, this signal here. Now the loop would be larger by this portion. So maybe now this signal would rather return, instead of here, it might return here and down, because there is another track up here. So let me show you that one maybe. So that signal which would return maybe here would rather go there. So going there to ground. So there is one way of going here or returning there. So here is the smallest loop, right? So it would probably rather return there. So you have to take that one in account as well. Or partially it will return here, partially here. Anyway, let me delete everything. Anyway, the currents would always find a way to come back to its source. And by gridding this signal routing in this orthogonal way, this is then ground grid and power grid. These grids allow all these signals to return by some path back to original source. But what if a signal is a high-speed signal? Let's say that one here. Let's say this one is a very high-speed signal, which takes power from power supply, goes here to ground, then it would return here back and up. That would, of course, take some area, but maybe we could rather go like that. Instead of return down here, I might also place another wire, another track just next to it, and it would rather return here. So that would be another option. And that would minimize the current loop for the most sensitive high-speed currents. I would say most sensitive, I would rather say most harmful. So if there is a high-speed signal somewhere, you should provide him some sort of close, short return path to minimize the current loop. And this is possible, of course, or mandatory, I would say, in this very simple double layer PCBs. Well, these times are now gone, and we don't have through-hole components for digital circuits anymore. We have because here are many problems. The power supply is always on here. The ground is also fixed to be here, and all digital chips were made the same. Power supply on top right, ground on bottom left. And these were then been able to connect very, very regularly. But this also caused a lot of problems bypassing, because now the simple area of that bypassing circuit itself, not accounting all the rest, is already quite large. And by that, you cannot bypass high frequency currents. So these circuits never were able to work at high frequencies, more than a few megahertz, like these first computers were actually made to work at. But this technique I showed you because we still use it in some sense, because if we make double layer PCBs, we just cannot have a continuous, well-defined ground plane. So we try to make it as well as possible. Like here, for example, we have a integrated circuit here, a microcontroller, and here is a to D converter. And let's say there is a digital line going from here and coming to this microcontroller. And then the return current goes to ground, which is here, and then follows this path but cannot go through there, so it has to go somewhere else. So it goes down here and up there, and then here it's already on ground, it has to go around and to this point where it returns back to the main ground pin. So if I have a ground layer, one thing is for sure, I have to provide a wire for this return current to go back on top layer. So here it goes from top to bottom, goes on bottom, and then it returns to top. But there is a portion of current that also can flow through this wire and then return on top layer closer, then returns back to bottom and continues there. And there must be a part of current flowing here, returning to top, going over, going back to bottom, and continuing here. So there must be several ways of this current to return back, and more ways I provide, the better my design is. So maybe I could also use this part here, which is now interrupted, broken. I can move these lines up, move these wires down, and I can maybe make a space for that part. So that's the solution. As you see here now, the return current flows from here and goes directly there, changes layers at many wires, going down and returns back to here and here. So just by moving lines a little bit, I can provide more space for the ground plane. And the ground plane should be placed on top and bottom, and then it should be well connected together with many wires. And by that, I make so-called ground plane grid. And this technique is called ground plane gridding, which actually in the most basic sense means that every piece of your PCB that it's still uncovered with copper, you utilize it for copper plane on top and bottom. You connect it to ground, try to move the lines around, move the tracks, move the wires, change from point to point until you find a big, nice, continuous mesh of top and bottom interchanging planes connecting whole circuit as well as possible together. And that would minimize ground plane impedance and also provide a lot of ways of the current returning back to its source. However, you cannot do that well enough if you have high-speed circuitry. A double layer PCB would just not work. You have to go to more layers. But first, let us look about or check the ground planes, how they operate and what they actually do. So the basic effect of ground plane is actually that it transfers this loop here. Now I have to change the color again. Pointer options in color, I would go for red. Yeah. So this loop is then changed to that one. If you provide a return path on bottom, let's say ground plane, your loop area changes a lot, which is the basic effect of the ground plane, with lots of others. So the first one, minimizing the current loop area. A ground plane is also called a mirror plane. So it can be called, instead of ground, it could be called a mirror plane. Why? The mirror plane is because the line, the track, which sits on top of that ground plane. So this is a dielectric, sees itself in a ground plane as in a mirror. So here is an apparent mirror image. And that field force lines are exactly the same as if there were no ground plane and there were another mirror image of the original track. Now, what does that mean? The line or the track has a very defined geometry. And this very defined geometry with continuous ground plane defines its basic electromagnetic properties. And the ground plane, of course, also provides so-called return path for the current that flows here. So if there we have a current that flows inside this line, the return current flows back on the other direction, just below the original line. If the track is then taken on the PCB in different directions, the return current always follows the route of the track. But here I'm talking just about high frequency return currents, because at high frequencies this proximity effect takes place. So how the currents flow? In a single line they tend to flow on the surface of the track, right? If you put a track over the ground plane, they actually flow closer to each other because of proximity effect. This is the skin effect here, the skin depth. Here is the skin depth as well, delta, and here as well. But the currents tend to flow just below this track because of this proximity effect. If I now have two tracks, let's say on the first layer, this is second layer, and this is third layer, the return currents of each of these tracks is just following the route below it. Now, these two currents can interfere. Depends on the skin depth as well. So it's advisable to move them apart a little bit so they do not interfere so much. This would then minimize the crosstalk between that signal and that one. And if I have differential signals like USB, this would be then D plus and that would be D minus. These two lines have a proximity effect here. So we have a differential signal there, but also we have a common mode part. And actually the common mode part is in general almost zero as a total, but as looking at each half, you would see that you have a current flowing here and that one flows out and that one flows in. So we have actually two current components just below each track separately, and for those current components you have to keep the ground plane still there. So also differential signals need a ground plane. All of these tracks which I showed you actually are so-called transmission lines. What is the transmission line? We will have a whole chapter, whole lecture about transmission lines. So now just quickly a peek into transmission lines. A transmission line is just a normal track on the PCB with a ground plane of some kind, and it transmits electromagnetic wave. That's each high frequency signal can be represented in a form of electromagnetic wave. And that electromagnetic wave propagates through that line. So it changes intensity, it changes direction, the current flows back and forth, and all that is, well, electromagnetic wave on a transmission line. And that wave has a certain speed. That speed is actually dependent of material properties of the dielectric, its permittivity and permeability. And if you take the speed of light, the speed of light is 1 over square root of mu h epsilon 0, mu 0 epsilon 0. That can be then translated to this equation. So the speed of the signal propagating below that transmission line is actually the speed of light divided by the square root of two main constants of this dielectric material, the permittivity and permeability. And usually the permeability is relatively 1, which would then lead to C over square root of epsilon relative. That would be a case of PCBs because the μr is 1. And each of such signals, so the signal propagating through this line, has a certain property. And we define that property by so-called characteristic impedance, which is a ratio between electric and magnetic field, or in case of tracks on PCB, that would be a ratio between the current and the voltage on the tracks, and is calculated like that. So it's actually, in case of the tracks on the PCB, square root of μ0 divided by epsilon 0 is actually the impedance of the free space. So it's the characteristic impedance of this free space. And then we have multiplied by the μ relative, which is 1. So what are we left? Only epsilon relative. And this is the z of the free space. And that z of the free space is 377 ohm. This is the impedance of the electromagnetic wave in free space. It depends only on these basic constants. So again, there are two main properties, which is the Z0, the characteristic impedance of my signal, and the speed of that signal. Now, the dielectric plays a big role here, but not only that, also the dimensions of the line. Let me show you. An ideal transmission line in electrical circuits can be represented as a LC continuous ladder. So these L's and C's are actually the lumped elements representing a short piece of transmission line, DL, and these pieces should be as short as possible, let's say dependent on the wavelength of the signal, of course, but much shorter than the wavelength of the signal, and then you can easily represent such a transmission line by that. And a lossless, without any losses, any resistivities here, a lossless transmission line has a characteristic impedance of square root of L over C, and this L and C is then in, let's say, nanohenries per centimeter, and C in nano or picofarads per centimeter. So that would be a normal representation of these two elements. Now, the signal propagation speed is 1 over square root of LC, and propagation delay, of course, the speed of the signal is here, and it's the normal physical formula. Now, more or less, these are then represented by the dimensions of the track. So let's say a track has a certain width, thickness of copper, dielectric constants, and so on, and all that is then influencing the impedance and the speed. So these are different types of tracks you can find on PCBs. They are taken from a software called Saturn PCB, and you can download it and calculate the properties of your tracks. So this is a single microstrip line. This is a strip line, but strip line can be symmetric or asymmetric. This is unshielded strip line, embedded microstrip also called, and this is a coplanar wave where you have ground on both sides and then wires connecting these to bottom ground. So the line which is totally surrounded by grounds. Then you have differential pairs, such as a differential microstrip line, or differential embedded microstrip, or differential strip line, symmetric, asymmetric. You have also broad coplanar shields and so on. So all that is a part of the big range of transmission lines which have defined properties. And calculating these properties, you can use several formulas which are empirical formulas, but you can also take the software and calculate it by yourself. And this is what I would like to show you. This is Saturn PCB software, and I would just go and calculate one for you. So I would go for conductor properties, and I would go for planes. Let me see. Here I don't have. I have to go to conductor impedance. Yes. So I will take a normal PCB, 1.5 millimeters thick, or 55, let's say, something like that. And I would go for microstrip line, 35 microns of copper, 18 base plus 18 electroplating. Microstrip line, epsilon of the FR4 is here somewhere, and width of 0.6 millimeter would give me 100 ohms. Sometimes I want 50 ohm track. They are usually used for antennas. 50 ohm tracks would require at least 2.8 millimeters to get 50 ohms. That would be a really wide tracks. So what you have to do, if you want to make 50 ohm track on such a PCB, you have to make it short, thinner. Let's say go to 0.5 millimeter. That would then, maybe you would only use one or less 0.8 millimeter wide track, or 0.9, I'm guessing now, to get a track which is 50 ohm track. So all that is very important to know, because when you are choosing your PCB stack, you have to know what kind of impedances of your tracks are required, and therefore you have to choose what type of thickness you would take. So that's just an example. I actually made a calculation for a microstrip line. A microstrip line, as I shown you, is just a line over a continuous copper ground plane. The copper thickness I took 35 microns. The height of the PCB is changed here, the thickness of the dielectric. The dielectric constant is the one took from FR4. And these are width of the tracks. Now if I want 50 ohm line, as I showed you, on 1.5 millimeter PCB, I need 2.8 millimeter wide track. Of course, for a normal track width, I would have to go to 0.2 or 0.1 millimeter thickness, which of course would already require multiple layer PCB, because such a thin 2-layer PCB is just not a way to go, because it would be too flexible, too thin, too fragile. Another good point of the ground plane is also the impedance of the plane itself, because the thing is, what I want with ground planes to minimize the voltage drops due to currents, because that would cause me so-called voltage generated common mode noise. For example, I just would like to show here. So if this is a ground plane, the current flows on that ground, it would cause a voltage difference, and that would then radiate through the air very quickly. So minimizing the impedance of my ground plane from point A to point B would also minimize the voltage drop, and therefore minimize the common mode current generated common mode noise. So decreasing the impedance of the ground plane is really very beneficial, and this is the change of the ground plane impedance from one track on the PCB with respect to a finite ground plane here, which is a 5 centimeter wide, and the change is more than 100 times of the impedance of the track versus the ground plane. If I used a continuous 1 ounce ground plane, I would go even 10 times lower. That would be an infinitely large ground plane. So by using ground planes, I really drastically decrease the impedance of that ground itself, therefore minimizing the ground loops. Minimizing the voltage drops on that ground. So besides minimizing ground loops with a continuous ground plane and having a really well-defined electric field on the tracks which define the electromagnetic properties of the track, I also minimize the voltage drop on that ground to minimize the current generated common mode noise. Now, let me show you an example now. This is an example with two ICs that are connected with one single line. Let's say we have a source here. So the voltage, high frequency part of the voltage starts with the bypass capacitor, runs to the chip, then goes to the track, and then goes to on the track, comes here, goes into the IC, then returns to ground, and then back. Now the question is how it goes back. If I have a continuous ground plane on bottom, at low frequencies, it would follow the least resistance path. The least resistance path is the most straight path. So that would be a low frequency return path. The high frequency return path would follow the least impedance path, which would follow the least inductance path. The least inductance path is the one which forms the lowest loop size. So returning just here, below the track, would be the least inductance path. That would be a high frequency return path. So the currents also, or the current as well, always follows the path which is the most beneficial in the form of its energy losses. And therefore it also always follows the paths which radiates the least. And at high frequencies, that would be path just under the original line. Now the question of course is, what can we do to provide it? Because that's the only thing we have to do. We have to provide that current paths and they will follow it, and we will be safe in terms of EMC. The change is drastic. That's the difference between the track without a ground plane and the track with ground plane. And the difference is in the range of 40 dB, which is enormous. That's 100 times better if you have a ground plane. You can have ground planes on 2-layer PCBs. You can have it, but then these PCBs should be quite, I would say, simple. This is a simple DVB-T antenna RF amplifier where the main use of ground plane is to define the electromagnetic properties of these tracks to have a certain impedance. And that impedance is required to have a maximal energy transfer from input to output due to this energy transfer rule, which says the impedances should match, and therefore you would get a good transfer of energy. If the impedances do not match, then you have reflections, and these reflections would cause problems. Well, in reality, it's really hard to assure a continuous ground plane in 2-layer PCBs because it's just too many tracks. Like if you put a track on bottom layer, like here, then this return path would not be able to follow. It would have to go around because the current wouldn't be able to cross it. Maybe if this track wouldn't continue up here, maybe it could go around somewhere and then go and return back. But here it would stop, then it would go around, probably like that, and maybe partially also through here, here, and here, then follow here. So you have to go from the source to the load through all the wires back to the source. And breaking ground plane below the original tracks is not a good idea if you have high frequency signals there. If you have low frequency signals, you don't care. At high frequency critical lines, you have problems. And therefore, you should make sure that below those lines, those tracks, the ground plane is not broken. You can break ground planes also by wires, like here. See, the signal cannot return through these layers, it has to go around. So you have to move wires a little bit so that the signal can go through it easier. Or maybe even make groups and bigger ground plane layers. And that's quite a problem in nowadays circuit, because we all want to use through-hole wires because they are cheaper. They are the most cheap they are. And of course, you have to use many wires if you have many signals. And these wires are then penetrating the ground planes as well. And these ground planes now become like a Swiss cheese. And there is a lot of space taken by these wires. So you have to sort of be careful how many of those wires to place and how to place them. Let me show you a few examples. The first example is shown here. It's a very old PCB back almost 15 years ago. Here is a A to D converter, and here is a microcontroller, and there is a high-speed signal going here. And now this high-speed signal goes here, and then it has a return path somehow. But here I used two tracks to shield it in some way, but I did not connect them anywhere. And that return path, if you follow it, it goes inside, then it goes to ground, which I think is here, yes. Then it follows this very thin line to here, then it changes layer, and then it goes somewhere, but it cannot go here, 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 anywhere. So it has quite a long way around, up there somewhere. So these two tracks here did not play any role at all. So that noise from that signal was interfering with the A to D converter, and it was not working well. So what I did, I just made a small hole here, drilled it, and made a short connection. Now, the return signal of that current actually was able to flow here on the same layer as the track, of course, but still it was much shorter, and that solved the problem. Here is another example of one of my students. He made high-speed connections through some optical isolators through this connector here. And these are the connections on top, and these are connections on bottom. As you can see, I have to change the color now. As you can see, I will choose yellow color. There is a track here, and it is breaking the ground plane on the whole height of this PCB. So let me show you how to follow the tracks now. Let's say this is a source. So the current starts here, follows this track somehow, I think it's here, yeah, going through here, finishing there. Now it goes to ground and then back. It goes and comes to here, then it cannot go any further, but there are 1, 2, 3 wires here. So let me show how the situation is on bottom. That wire is on the other side of the track, luckily, and these two are here. So the return current cannot go there. It actually has to go on top. So the loop size is like that. Here it turns to bottom, and it goes back. Where? Well, it can go here, but there is no wire there to return back on top layer. Here, this is the ground pin, this is the ground pin, and that one. So it has to go all up here to this wire, change layers, and then return back to the ground pin here and here and here. Quite a long way to go. So what we did, we actually replaced a little bit, just a few things. We put a few wires extra. That was also by like 10 years ago or so. And also we moved this track from here to the edge, so that these ground connections were here at this side. And now there was a continuous ground plane to the source, but also here are wires. Here, 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 here. All the wires that are connecting the ground plane to the top layer when it can then return back to the ground pins of this microcontroller. What else? USB connection. This is a bad idea from one of the students. These are two USB signals. They go through some small resistors and then go here to this chip here. I would never even draw it. So that's one USB, that's another USB. Sorry, no, these are two USB signals. Yes, these two. As you see, the ground plane below them is just awful. So if this is the ground connection of the pin here, you see that it even doesn't have a connection on bottom layer. So the areas, the loop areas are like that. Where is the ground now of this chip? I think it is here. So that this is the returning. So there is one wire, but then its return current must go to here. So this wire doesn't play a role at all. See? Now he has an interrupted ground plane here, here, and it's all like a big nonsense. So that's a no-go. Another form of the USB connection, much better. The signal is forming small loop differentially, but also on bottom it has quite continuous ground plane instead, except here. But let me show you how the current flows. It flows here, there is a problem here, a problem there, but not that bad, because the return current comes to this pin, which is a ground pin, returns back to this wire, changes on bottom layer, then it can follow actually the currents of these two layers. Here it will go a little bit around and then follow back to this pin where we have the wire to connect the top layer again to this connector. So there are small interrupts in the ground plane, but not that severe. And this is this is a very good solution. These are two USB lines coming to here, returning to ground. This is a ground wire. Then we have a return current just below here to this ground pin. No interrupts. Well, I would like to show you another high-speed USB connection. In this time, it's USB 2.0. If we were talking here about USB 1.1, which runs at 12 megabits, so the frequency is 48 megahertz. In these two cases, that one runs at 480 megahertz. Quite a lot. The required differential impedance is 90 ohms and the common mode impedance is 45. And at this track length, it's quite important to keep them. In order to do that on a two-layer PCB, it's quite tricky because actually you have to make quite wide PCBs. You know now why? Because if you want to make a 90 ohm differential and 45 common mode, that would mean around 3 millimeter wide tracks, which is enormous. But we did it by using coplanar waves. A coplanar wave, as I told you before, it's a way how to make a normal track with a low impedance. So what do you need? You need wires next to the track, left on the right side, and ground planes on top and bottom. So these are the wires. These are the ground planes on top and bottom. Here it's all the time continuous ground plane on bottom. And the tracks are wide as far as they can be. And their lengths are matched, as you see here. Since this track has shorter path, here this track is then widened. It has a few turns before it hits the target. And this is then prolonging the track length. And this design actually works, even though it's made on two-layer PCB, and I don't know whether it meets the EMC standards as well, because I'm quite sure that it has problems with that, but never tested it. But it works electrically. When we did it like that, it didn't work because the impedances were not correct, the lengths were not matched. And here, most of the tracks have right impedances. And at such high frequency, this is important. Now maybe it's a good time to show you a few, or to explain to you why the impedances of the tracks are important. The thing is that this is so-called signal integrity, which deals with that field, that area. The signal integrity means that you want to keep your signals as well defined as possible. So if that's the signal on your digital line, you want to keep its shape as close as possible to the source. So not, I would maybe rather draw a little bit differently. So ideal digital signal would be something like that. But this is, of course, is not achievable. So in reality, what we have is something more like that. You all know the trapezoidal approximation of the digital signal. Now that is also acceptable, but what is not acceptable is ringing, which can happen quite often, or too smooth, so that signal is not even reaching the logic level, coming more to a sine shape, and so on and so on. So the signal integrity field is all about keeping the shape of the signals as close to original as possible. And the impedance of the tracks is one of the main properties which would, if you keep them to a level which is defined by the source and the load, you would keep your signal as close as possible to original shape. And we will have a whole lecture about that, so don't worry, we'll come back to that. Just now you have to know that impedances of the tracks at high frequency interconnections are very important. And you can keep the impedances of track very defined by defining its geometry. So if that's the track on the PCB, you should have a very well defined geometry. So very well defined ground layer, a ground plane, and defined surroundings of that track. And this would then keep the electromagnetic field of the track very well defined. And this would then define a very stable impedance. And that would assure signal integrity. Now we will move to multilayer PCBs, because I think that we did enough of these double-sided PCBs. So we will now go to multilayer. And first I would like to show you an example. So why would someone go to a multilayer PCBs? In multilayer PCBs, there are several advantages. Because you have more layers, you can spare a ground plane on the whole layer. So for example, here, since you have multiple layers, you can have a total ground plane as a one single layer. You can have also total power supply plane as a one single layer as well. And then you can utilize also the capacitance between those two as a well-defined, high-frequency, very quality capacitor. All that, including all the tracks. So 4-layer PCBs at least would already make your life much easier. And it's much easier to make them, to design them, not to make them, just to design them. But who cares? Because producers are caring for the manufacturing part. So I would like to show you a comparison. This is a 2-layer PCB and this is the 4-layer. So that's the 2-layer and this is the 4-layer. This is the 2nd layer among 3 and this is the 3rd layer among 3. So what is shown here? It's a digital low voltage interface between the microcontroller and the display, 24-bit connection. These are high-speed signals and they should be, I think, 90 or 100 ohm impedances. But these are certainly not, because that's a 2-layer PCB with a quite large thickness. So you cannot achieve such impedance by these narrow tracks. They would have to be wider. But nevertheless, we tried to make it. And actually it was working. It was not a problem that it wouldn't work. The problem was that it had too much of the electromagnetic noise. So these are these connections. As you see, because these connections have to be at least double-sided on 2 layers, then you just don't have a return path well defined. If this current flows here, then it returns back on bottom, but here the bottom layer is interrupted, it's broken. And these are layers, these are tracks on bottom, and here the top layer of these tracks is interrupted as well. So there is no continuous ground plane anywhere possible here. But if we move to here, this light grayish yellow area is a continuous ground plane for the red tracks. And this bluish area is continuous ground plane for the blue tracks. So these two, if the tracks are on bottom, this is the ground plane for them. If the tracks are on top, this is the ground plane for these tracks. So each track has its own ground plane. And this makes them well defined. What else? Ethernet. Ethernet is a differential signal connection. And the impedance of the Ethernet lines also have to be 100 ohms, I think. So these are these two differential lines, transmit and receive, and going all the way to the microcontroller there. And you see they are routed on bottom layer. So here is a problem now because the top layer is interrupted by these tracks here. But we put a lot of wires to go see continuing on bottom layer and then changing layers on top and bottom, and so on. So these are so-called ground gridding part. So then we went on 4 layers, and this is a continuous ground plane again on this 3rd layer. So this is the ground plane on 3rd layer, and on 4th layer we have the USB lines. And again, they have very well defined ground plane. And we also taken care for the length tuning. So all the tracks on the same layer pair are of the same length. Okay, the power supply is also very advantageous if you have 4 layers at least, because this is a 2-layer power distribution network. And here on the 4 layers, you can have the whole plane or part of the plane devoted to power supply, which makes a really good capacitor between the power and ground, which acts as the best high-frequency capacitor possible. And all that contributed to this result. This is a 2-layer PCB EMI, and on the other side we have a 4-layer PCB EMI. You see the difference? These are the peaks, and that's the change. That's the difference. The difference is more than, here it's more than, I think, 26 dB. And here is around 15 or 16, at least. So that's a lot. That's more than 10 times better. Just by using 4-layer PCB and confining all these tracks with the ground planes, defining their current loop sizes, and defining also their impedances. So, encouraged by that, we will go and discuss and talk about multiple layer PCBs, how to choose the layers and what are they for, and so on and so on. This would be done in the next part of the lecture. See you soon.